So I'm going to do a quick walkthrough of Chapter 9's already filled in notes. Sometimes it helps people just to have someone walking through and talking through the notes with them. This first page of notes is a reminder of what energy is. There's some homework topics on this, but this isn't directly going to be on your test. Energy is the ability to do work or supply heat. Work is negative pressure times your change of volume. Heat is represented with Q. We're going to get more specific with Q later on. And the unit that we're going to be using for energy is a joule. Be careful, charts can be in kilojoules, calories with a big C or with a little c. We'll show those later. Potential energy is energy because of your position, like the top of a waterfall, but kinetic energy, that's like falling water from a waterfall. Had a simulation in this that we watched, and just remember you can convert between all these different forms of energy. This chapter, you're specifically doing conversions between chemical and thermal energy. Don't forget that this triangle right here means change, which is final minus initial. There's some comments in here about work. In Gen Chem 1, we're focusing on this first condition, but you can also have a second condition if you have a bomb calorimeter, which is like a sealed container that won't let the pressure out and won't break. Also, there are state functions: enthalpy, internal energy, pressure, and volume. And a state function is just that it doesn't matter the path you took to get from the beginning to the end, but you have the same result every time. So I was talking about like budgeting, and you could spend it all at once, or you can spend it in pieces. In both cases, you still end up with 0. So the final minus initial is still 0. You could even have earned some and then spent it, but the final would have been 0. You should know the law of conservation of energy. It's like the one of mass. Energy is neither created nor destroyed. After a phase change or a chemical reaction, there must be the same amount of energy as there was initially, but it would be in another form. Thermodynamics is the study of thermal energy. We use Q to represent heat. Phase changes is Gen Chem 2. Reactions is Gen Chem 1. This right in here, potential chemical energy, is because when atoms bond and share like this, they don't have that line in it. They're sharing when they overlap. That's a lower energy state, and they will give up a little energy to make that happen. So when they form a bond, it is a energy release that happens. And then when you are breaking bonds, that means that you have to add energy because they were lower energy. You have to add energy to pull the atoms apart. And that's why we say energy is released when bonds are formed. It's an energy releasing process because it's lower state. And it's absorbed when they're broken because you're pulling them apart. And you have to have energy to pull them apart. We had a big to-do about heat and how it moves in one direction from hot to cold. Reminded everyone that negative Q is energy out that's been heat moves in one direction from hot to cold. Negative Q is energy out that's been released. Positive Q is energy in that's been absorbed. So this negative doesn't mean particularly that it's below 0. It means that it's outward energy. It's directional. And then the positive is inward energy. And we have this picture right here with these Qs going, with the negative Q, it's going away from what's negative Q and into the thing that's positive Q. Big key point, they keep doing this until they are at thermal equilibrium. The funny little phrase, shut the door. You're letting the hot air in because hot is what's moving. The kinetic energy is what makes things hot also. So like things are vibrating and moving even faster the hotter that they are. Or you could say the hotter they are, therefore the more energy they have, and therefore the faster they move. But once they touch and get in contact, they transfer until they reach thermal equilibrium. So thermal energy is kinetic energy associated with random motion of atoms and molecules. Temperature is how we measure it. So heat is the energy, and temperature, we measure the temperature changes of heat energy. So if it's hot, it's going to have higher kinetic energy. And again, they go to thermal equilibrium. Then we did a comparison of heat capacity versus specific heat. So heat capacity is when you have like standardized things in industry and they only come in certain sizes. So you don't have to know the per gram specific heat. You just know that the big skillet, the large size one, has this heat capacity and the small sized one has that heat capacity, or coils or whatever you're talking about. It also comes with bomb calorimeters are like this too. They come in different sizes and they come with a heat capacity associated with their entire size. You don't have to weigh a bomb calorimeter and figure out like how many, I don't know, grams it has and figure out a gram per amount. The entire calorimeter has a heat capacity. And as a little note, this was on Newton, and I'll just throw it in right over here to the side, is that if you have something with a heat capacity, it's a big C. And to figure out the Q of something that already has a heat capacity, it's the big C times your change of temperature. You don't have to multiply it times mass because the big C already takes that in consideration. So heat capacity is the big C. Specific heat is what we deal with in chemistry because you can weigh out all different amounts of stuff. You can have a gram, a half a gram, quarter of a gram. You weigh out things. And so we need the specific heat to be per like mass or per mole. Notice you can use an S or a C. Our current textbook is using a C. And both of these are measured in terms of how much they raise the temperature by 1 degree. But the specific heat, again, it has this gram unit or mole unit that it's subdivided into. So specific heat, the small s, the small c subdivided. There's a different word if you're talking about the per mole version of it versus the gram version, specific heat versus molar heat capacity. And it's just the key thing is the units are going to be different. So if you're grabbing numbers off of the internet, you're probably going to want to be grabbing the specific heat capacity numbers to match up with our equation that you're going to be using. Q equals m times little c times delta T. That's the one that we're going to be using mostly. So we just had a review of that, and then now we're going to actually get into doing calculations. This is one little thing, is with the specific heat capacity, the larger the specific heat capacity, the little c, the more energy needed to increase the temperature by 1 degree. And also, the more energy released when you decrease the temperature by 1 degree. Things with a larger C will be able to impart more energy to other things also because it's more energy needed. It'll be able to, if you have two objects at the same temperature, so if you have two, but they have different C's, and you put them, you're trying to combine them with water at room temperature or something, then the one with the larger C will give more energy and increase the temperature more. And then we had a visual, we talked through this. The main point is right in here doing these equations. The first part is using this MCAT and just making sure that you know what you're talking about. This Q is going to be the thing that's the joule, the M is going to be the thing that's in grams, the C is going to be the thing that has more than 1 unit, and then this is going to be your T final minus T initial. Just keep in mind you can have a little calorie is equal to a big joule. You can have a food calorie, which is a kilocalorie. You can say in 1 kilocalorie you have 1,000 joules. Don't forget about how to change from Celsius to Kelvin. And this was a big one in purple. A lot of people by this point in the chapter have forgotten that density of water is 1 gram per milliliter. And that means that if you get 60 milliliters in the problem, that for water, you can also say 60 grams. So then we just worked through a lot of these problems. I suggested making sure that you write the amounts on the side. I like writing the TF minus T initial like this so that you can really see how the sig figs work out. The more complicated versions follow where you get both sides, the MCAT equal to the MCAT. So here you go. You just keep up with your units on the side. Did a quick review on how to put it in your calculator. This one was unique because everything was in Kelvin, and that's okay. When you subtract temperatures in Kelvin, you still will have the same temperature change as Celsius. You can pick some numbers and try that with it to prove it to yourself. Then we talked about enthalpy, and enthalpy is that number you write at the end with a triangle, and you can also include it in the equation. You don't put negatives in equations, and so it's kind of like saying the absolute value if you want to think of it that way. But we know that negative means energy out, which means product. So we put these in here. Even though it's a negative, we put it in as a positive, knowing that when we write it on the outside, it's negative. Delta H's can be positives or negatives. But if we're releasing energy as a product, then we write it as a positive. Also, when you're doing these, make sure that when you do conversions to grams, you don't end up with negative grams, because you can't. You can't have less than 0. So this is endothermic. This is exothermic. Endothermic has a positive, and you would write it as a reactant. Big exciting thing is now that we have enthalpy, it's a way to relate energy of a reaction to each individual mole amount of reactant. So we did a problem with that. And then we did some problems where you take any energy, so they give you energy in the problem, and then you practice converting that energy into moles using the delta H and whatever the coefficient was that you were given in the, that they were talking about in the problem. Then we have more of these problems. This one was kind of an interesting one. We spent some extra time talking about. You may want to review it in your notes. That this was basically hooked two numbers together, grams per or kilojoules per gram, and you want to make it into kilojoules per mole. And then we talked about how you have HF values in here, and how these are all HF reactions, but they are specific ones. So this is when you're figuring out the heat of formation of something. So it's really how you determine heat of formation as a reaction. And the key thing is that it has to be only one here, and that all of the coefficients don't matter so much, but you need to make sure that you only have elements, not compounds or molecules. Also, everything has to be in the correct phase. Then we circled the things that have a delta H of 0, which are elements in their normal states. And the ones we left out were things that either weren't elements or they weren't in their standard states. Then we said, hey, you can figure out delta H for a reaction from HF values, even if they aren't all in the element forms. So what we do here is we do products, all the products added together minus all the reactants added together. And so my little hint was make sure that you write your coefficients down before you write out your energy amounts beside it. And then it's products minus reactants. So my other key bit was that your H of reaction, put it below the arrow, and then you'll be much more likely to remember where your products are. We did some example problems with those. Those you just need to make sure that you're practicing. Then our last little bit was Hess's law, and this was 2 parts. One was that you need to know that you can reverse any reaction. You just need to make sure, see where my C is, you can flip it. Just make sure you flip your sign. You can also multiply or divide. So if I start off with this amount and everything's 1, I can use 2, 2, 2, and multiply my delta H by 2, and that's totally fine. You can also do it with like halves, so it's like you're dividing. Just make sure your delta H is by halves. The other piece that we were saying, it's in this picture here, is that when you combine reactions, you can cancel things that are on opposite sides, like the ABs and the Bs, and then the A's, they're on the same side, and you can add those. Then we had kind of a method for doing these. It was the idea was that you got to make sure you identify your overall reaction. Once you got that, then you make sure things are in the right places. So for example, the C was in the wrong place. That told us that we would have to flip. And then our CO2 was in the right place, so we didn't have to flip. That was fine. Then we need to check the amounts in front and make sure that everything is the right coefficient. So this is 1, that's 1. It looks like everything is the correct coefficient, so we don't have to do any multiplying on your H's. Once you've canceled the things that are opposite and you've added the things that are the same, You need to make sure that this equation matches the one on the left, and it does. If that's the case, then and only then can you add all your H values. If you have negatives, that's fine. You're adding negatives. And then we had some really long examples to make sure that you had this completely down. And that's the end.